CFO once asked me, how much insurance do we need? A condensate pump was undergoing maintenance and a pressure safety valve was removed. The pump was restarted without the valve, leading to a gas leak. Miscommunication during shift changes exacerbated the situation, and the lack of remotely operated isolation valves prevented quick containment. The gas leak ignited, causing a massive explosion and fire, resulting in significant loss of life and property. An explosion occurred at the Clean Energy Systems power station. The plant was a 620 megawatt combined cycle gas and oil-fired power plant. The explosion happened during a procedure known as a gas blow, where natural gas was being purged from a pipeline. The blast killed 6 workers and injured at least 50 others. The explosion destroyed the turbine hall and caused significant damage to the plant. So, welcome to MFLs, PMLs, and we're going to understand risk, and we're going to talk about loss estimates a little bit. And we'll start with definitions, then we'll get into the calculation process, how we do these calculations. Then we'll talk about some examples from actual risk engineering reports for power gen and for refinery. And we'll look at the challenges that face those who conduct these type of studies. And that's right, what we're doing here is we're estimating something that, or we're building estimates that are calculated. And there's some method to the madness, basically, is what we're saying here. And there are a lot of definitions, so let's get into it. The definitions that I'll be working with are for maximum foreseeable loss and for probable maximum loss, the two that are most commonly used here in the United States. I've spent some time abroad, working with folks abroad, and realized that sometimes we even use phrases that sound the same but mean something different. So anyway, we're going to break it down to just PMLs, MFLs. One of the things you need to be aware of is that some of these are the same as each other, and some of them even have two different definitions for the same acronym, PML. We're going to talk about when PMLs and MFLs equal each other, that makes the insurers nervous. And what does that mean? Well, the PML is something that you kind of are not surprised can happen to a plant. The MFL is something that you're surprised if it happens in the industry. And you've heard of them happening in the industry, but they're shockers when they happen. So if they're equal, if the odds, if the likelihood, the amount, if the risk of those are the same for your facility, that means that you're expecting to have the worst catastrophe, a lifetime event at your facility. So they don't like them when they equal. Now, give you a little formal definition, but explain it a little bit. The PML basically means when your initial line of protection is out of service, whether it's manual protection, whether it's a fire brigade, whether it's a sprinkler system, they're not there. That sprinkler system's out of service. What is there? The delayed response. They can get to the area in a certain amount of time, giving it the fire chance to grow. The sprinkler systems next door are working, so in a PML situation, that's what we've got. The primary system is out of service. Okay. Maximum foreseeable loss. What we're looking at here is all the active protections out of service. Everything that, from people to automatic fire protection systems, none of it works. You have to just count on separation distances to keep equipment safe or components, or passive fire protection like firewalls. You will get credit for a barrier because it doesn't have to turn on, doesn't need batteries, and works day or night. So that's what an MFL is. It's when that's all you're counting on. It's just passive protection. Now, the process of calculating an MFL or a PML is very similar. And, once you've defined the scenario, that's sort of what takes you off onto either path, PML or MFL. Once you've defined that scenario, now you're going to take a look at the how you calculate the outcome. So the process of calculating the outcome starts with that scenario, but then we have to model it. What is it that scenario turns into? Fire, explosion. And then we take a computer and we ask it, well, develop this fire and this explosion, develop this vapor cloud into something that ignites, and feed back to me what the results are. We'll input factors like separation. We'll model this, and then we'll decide, do we have any potential for this vapor cloud to impact that part of the equipment or property? So once we've done a little modeling, we look at any kind of separation or protection. Then we get into valuations, and I'll talk some more about valuations, but this is part of the process for calculating the MFL. We need the valuations to have a legitimate, maximum foreseeable loss calculation. And then we're going to look at damage. Some MFLs are very simple and just apply a flat percentage to value of the building or facility or equipment, and sometimes they're a little bit more complicated, and we'll show you the difference here between a simple one and a complicated MFL study. Some of the things that can complicate MFLs, we will talk about those as well, and then we'll talk about a step-by-step process to get you through the whole concept of performing a MFL study. This is not a study. This is everything that you need to think of when you're performing this study. Alrighty. So first off, we want to talk about the scenarios, right? What can go wrong, right? Well, answering that question, pretty much anything, if you can think of it, it can happen. And what has happened can happen. Now, this is a list that is kept up by Marsh. They do an awesome job at tracking large losses in many industries. You can see most of these in the one Piper Alpha that we already described in the beginning, $1.96 billion. And you can see that it drops off down into the hundreds of millions there before we get off this page. They have a study of the top 100 large losses, and the study drops down into much smaller losses. The largest power gen loss that we see is usually in the maybe 100 to 300 million dollar area. The largest losses that I personally have been involved with were 600 million. They were 600 million, and they were back-to-back years of oil production shut off in the Gulf of Mexico. Back-to-back full limit losses, and we only collected 50% of what we were due, because we had to adjust the losses very quickly to make payments on contracts that we had sold forward. So all in all, we paid 24 million, collected 600 million, but that took us out of the market. They wouldn't sell us insurance anymore for shut-ins from hurricanes, and we had to sell the business units. They ended up selling them, made about a $12 billion profit on all of that. So good news, bad news. You don't know what's good and what's bad, right? Well, what drives the losses besides hurricanes? We know what hurricanes can do, but what drives losses in these facilities that drive all these MFLs? Once you have an idea and a clue of what that is, and I know the engineers want to look at it from the standpoint of, if we know what's driving this, we can prevent it. I get that. Okay, but now we also want to know what's driving it so we can get an idea of how expensive is it going to be? Is it really likely going to happen? So we want to know more magnitude and frequency when we're asking what's driving these losses, okay? And, if we look at the specific ones that are very large that are covered, what I did was used artificial intelligence to basically help me go through the report from Marsh, the 100-year study, and pull out the lessons learned from the actual events that were discussed. And it looked at some of the major events, and it pulled out the lessons learned, and these are the common lessons learned. You can see equipment failure. The events were Piper Alpha, Deepwater Horizon, and Big Spring. But human factors and emergency response and preparedness. Okay, these were the top 3 drivers of our MFLs. Now, let me pause and reflect and get out of your way, give you the slides. So, if we stop and ask ourselves these same, type of questions about, are there historical patterns, are there system vulnerabilities, human error, maintenance gaps, design flaws, operational changes, training deficiencies, communication breakdowns. These are the kind of things, the categories and the kind of questions that we can ask to make sure that we're really assessing the worst that can happen at our facility. So let's get going some more front end slides. There we are. So now that we've got these scenarios identified, our next step is to calculate the damage. And we're going to do that by running these things through some models. There's fire models, there's vapor cloud models, flax models, vent tree, blast wave, damage assessment. Let's take a look. Here's what a flax model looks like, and this is less than a second after a natural gas release on an offshore platform. You can see the fireball there, the flame, and the flame front burning through that fireball back to the sources of ignition. The other things that we have available, fire dynamics simulator, and I'll say that these models were available when I was going to college, which was about 40 years ago, somewhere in there. So it's incredible that, we were still using punch cards for some of the computer science stuff that I was learning, and now we're still using some of the things that we learned about back then. The Nuclear Regulatory Commission has a fantastic document, New Reg 1805, and if you Google that, I'll give you the link to it, but it's probably easier just to Google that. But you see that they have many of these calculations. They've got actual spreadsheets, live working spreadsheets you can download to run these kind of calculations. Estimating the burning characteristics of liquid pool fire. How many of us have that in chemical industry, in the power industry, transformer pool fires, right? We can calculate now the heat release rate, the burning duration. How long is the fire going to last? If we spill the liquid out of this tank and it can, fill this room, how long is that fire going to last? We can do the radiant heat flux from a pool fire and determine, will this tank be exposed from the radiant heat from this tank? So it's phenomenal. The website or the tools are called Fire Dynamics Tools. The site's down there at the bottom. Those of us with battery rooms wanting to know, are our ventilation fans adequate? This will calculate the hydrogen generation rate of battery rooms. So pretty good resource here. Good to look at for calculating MFLs. Now, after we've modeled the damage and we know what's going to be broken or burned or exploded, then it's time to add it all up. And initially the premiums are used to, our values are used to give us a rule of thumb on what the premium's going to be. They'll just multiply our rate times a value, and that's a premium. And then it gets adjusted based on loss history and exposures, and tweak it for technology, tweak it for risk engineering. So there's factors that can tweak those rates. Well, in a damage or percent-based model that looks at just 50% of this building's destroyed, you would look and say, well, that building is $100 million. It's a $50 million PML. So that's kind of just a straightforward, easy way to apply a percentage to a building. Sometimes it's a little more detailed and it gets into more specific pieces of equipment. And we'll show you sort of a simple MFL summary and a more detailed calculation. Be careful about business income. The policy will tell you what the period of indemnity is. I've seen 12, 18, 24. I've seen the MFL calculation at 18 when the BI in the policy is 12. So don't get hooked up on just what the MFL in the policy or that BI or that waiting period that they're analyzing is in the MFL study. If you really want to know your coverage, look at your policy. And so it'll drive protection decisions. So you can go out and spend money to manage risk a couple ways. You can add protection or you can buy insurance. And we found when I was at a company that ran power plants that there's some insurance you can't buy. The cost of the insurance to pay back the loss of income when a power plant shuts down exceeds the cost of what anybody wanted to pay to get rid of that risk. But it did justify a $5 million a year budget for me to go out and put in protection, risk engineering projects across a fleet of 27,000 megawatts. So, it was a way to get some attention. This is a huge risk that we face. Insurance is way too expensive. Risk engineering can do the job. And oh yeah, when you pay that, $24 million for your insurance policy at the end of the year, you got an expired piece of paper. you give me $24 million for risk engineering projects, and at the end of a year, you've still got all those projects, right? So that's sort of the sales pitch for risk engineering and solving these protection decisions. Now, we want to do valuations, and remember that they need to be adjusted. They can go up or down, that inflation can have multiple effects. And let me tell you that sometimes inflation can make it appear that something is worth more, and then sometimes inflation can make something worth less. Let me give you an example. The cost of oil goes down, and then the owners of refineries sell their equipment because they don't want to operate losing business. So the people that end up buying them are smaller companies operating pieces and parts. They don't have the same corporate overhead. They don't have the same backup structure. They don't have the same resources for corporate engineers. So maybe they don't run and operate as safely. That happens in a period of lowering prices, right? That you might have a problem with less safety or more risk. In a period of let's look at inflation from the standpoint of one industry, the power generation industry. You've got electronics, and the cost of electronics continues to go down. You've got the cost of labor goes up, right? And that pretty much continues to go up. And if you look at a substation outside of a power plant, the substation was built by taking electronics and setting them on concrete pads. The power plant was built by erecting forms, pouring molds, putting the concrete into walls, putting in steel, structures, welding, tanks, equipment, components, cranes. A lot more labor, a lot more money on the power plant side. On the substation side, the cost of everything has just come down. But if you are operating substations and reporting values based on handy equipment, inflation, escalation, or on a general inflation escalation that doesn't account for the difference between a substation and a power plant, then you need to go back and relook at your values. But neither with that. We need to make sure that our values are adjusted properly and that we're using good values for our study. That's usually the last piece of data we get. The engineers usually get it last when they ask for it. So now let's look at some example MFLs and PMLs. Here's straight out of a power generation facility, and you can see without the name for the equipment, which isn't a big deal. They're not the client. The client name is confidential and protected. But this equipment kind of just shows you that the size, and we're talking about the scenarios and what the events can be. And this is a summary, and it gives you an idea of how long it'll be shut down and what the costs will be in dollars. There, $4 million for a normal event that they expect to happen that we've probably already had happen. The PML is something that, $50 million, and that's something a fire in a gas turbine enclosure. And the MFL or EML would be the uncontrolled fire under the turbine, and that's with everything burned up. You're looking at about $100 million at this facility. Now, let's look at, this is power generation. This is boiler machinery, not just fire. This is the mechanical or equipment breakdown, but similar amounts and magnitudes, just not fire. This is blade failure, first row, resulting damage to all rows. So it's giving you, more mechanical breakdown losses. Now we're looking at a refinery. We're still looking at the power plant, but this is natural cat, and we're looking at the 100-year storm versus the 500-year storm. Now looking at a refinery, and the MFL here is going to be vapor cloud explosion. The arrows are trying to call out that it's a explosion that we're going to model here. So the neat thing about this is that it takes in a lot more data, right? It's not just what's the value of the facility, it's how much propane. 8,000 pounds of propane are released in this model. They run the model, and then they try to figure out, where's the damage. And you see the circle in blue is a smaller circle in the middle there at the top of the screen. It's the primary damage, and then you've got the other areas of lesser damage. And then you go through and you multiply the damage times that piece of equipment, and then you determine what your total overall property loss could be. And then we move on to a loss that would be more of a PML in a refinery. And this is going to be the first fire protection systems out of service, but the brigade gets there, and you can see the magnitude on this one. Still could be pretty high in a refinery because we've got so many combustibles and very hazardous facility. Now, are there any challenges to running these models and conducting these surveys? Well, heck yeah, there are. They're complex. People are involved. We need technology. It changes from the time you start writing a report to the time you come back. Regulatory issues, financial implications. Let me tell you that when you find out that that a facility's values have gone from $3 billion to $2 billion, and all your credit ratings were based on owning $3 billion worth of assets, you can raise some eyebrows when you report something like that. You got to work with very many disciplines, because you've got to bring this all together, because it's financial, it's engineering, it's risk, it's fire, it's explosion. So there are a lot of groups involved. So where do we start? Start where you are. Now I'm going to run through these pretty quickly. You can go ahead and I'll get out of your way. What we'll do here is let you screenshot them if you want, but we're going to need to gather these 10 steps in order to put together a great MFL report. Need the plant information, type of plant, capacity, layout, operational data, equipment and process details, critical equipment list, process flow diagrams, utilities and support systems, fire protection and safety systems, fire protection systems, fire risk assessments, safety systems, inventory, hazardous materials, MSDS sheets, location, historical loss data, past incidents, cause analysis, repair and downtime costs, surrounding environment, proximity to population centers, natural hazards, external fire risks, financial data, the replacement costs, business interruption values, insurance policy details, emergency response and continuity planning, emergency response plans, drills and training, business continuity plans, regulatory and compliance information, regulatory requirements, inspection reports, permit documentation, expert opinions and assessments, consultant reports, vendor information, industry benchmarks. And with that, let's just say it was fun, and thanks a lot. Come back the next time. Make sure to like and subscribe and share. All that stuff does is just get your videos like this. It gets my videos out to people like you. It doesn't get you bombarded, so please try. We'll talk to you later. Oh, by the way, I only need a few subscribers to get up to over 500. And I'd really like to do that, so that'd be pretty cool. And I know that the majority of the people who watch my videos are not subscribers. It's like a 2-to-1 ratio of non-subscribers to subscribers. So there's a target-rich environment. Come aboard and help to build the channel. Appreciate it. Thanks.